So here's a graph of f of x, and what we're going to do is we're going to look at that graph and sketch the graphs of the first derivative and the second derivative based on the data that we have for our first derivative. Now some things, when we graph things, are not going to be perfect. We're just going to do a sketch, but we're going to look at what are the key attributes that we know from our original function and from our first derivative and our second derivative for graphing this. So in this one, here's f of x. When you have your original graph, one of the first things you're going to look for when graphing your derivative is, does my original graph have any maximums or minimums? Yes. I have a maximum on my original graph right here. Now, if that is, or not maximum, I have a minimum on my original graph right there. If that's a minimum, what do we know about the first derivative? Again, what is the first derivative? The first derivative finds the slopes of all the tangents at any point on a graph. So if I look at that point, my minimum, and I drew a tangent line at that point, it would be perfectly horizontal. And if it's perfectly horizontal, what is the slope of that? It's going to be 0. So we know that at this point, my derivative, so I'm going to color code things here, my derivative here is going to be 0. Now, when we were graphing and when we were sketching our graphs, what did we do? Well, we had our original function, we took our derivative, and we found out where it was equal to 0. That's this point here. We made a sign diagram, and we put that point on our sign diagram to say that's where it was equal to 0. Then we plugged values into our derivative to find out where our original function was increasing and decreasing. So you might remember that we would have had a sign diagram like this. We would have plugged a value into our derivative and got it to be negative. This would have told us that our derivative was less than 0 and our function was decreasing from left to right. And then we would have plugged in a value after this blue point and found out that our function was increasing. What we're doing now is sort of working backwards. We already see the graph of our original function. We can see that it's decreasing until it gets to this minimum and then increasing afterwards. But now we have to say, how does that apply to our graph? It means that before this point, f prime of x has to be negative. And after that point, f prime of x has to be positive. Now that's a general sketch. My slope of my line might be steeper or flatter. It might have more or less slope, but I'm just using the idea that if I took my derivative has to be negative before that, so that means below the y-axis, and positive after, that's going to be above the y-axis. Other things that I would do when sketching this graph. I would say to myself, my original graph, what would you guess my original graph to be? What kind of graph? Probably a parabola, right? So if this is a parabola, what would the derivative of a parabola be? It'd be linear. So I would need my graph to be linear as a result. So I think it's always easiest to use this process to take a graph and then go to the derivative graph by looking at first, are there any maximums or minimums? And then plotting those points where it's 0. And then think about drawing your sine diagram off to the side to find out where is my derivative negative and where is my derivative positive. You can also use the shape of the original graph to give you a hint what the shape of the next graph is going to be. Now that we've got our blue graph, we can say, let's try to find our second derivative. Well, our second derivative is just the first derivative of the first derivative. So we can use our blue graph that we have there and use the same ideas that we have for graphing our red graph. Does our blue graph have any maximum or minimums? No. So on our red graph, there would be no points on that line. What do we notice about our blue graph as you go from left to right? Can you see that it is always increasing? That would mean that the derivative of the blue graph has to always be positive. So we need some sort of graph that's always positive. Now, what happens when you draw a tangent on any point on a straight line? You get the original graph, and the slope of that tangent will be equal to the slope of that graph. So using our estimations for what the graphs are, we said x squared, the first derivative would be 2x, the second derivative would just be 2. And that would be a straight line like that. Some things about the second derivative. If your second derivative is always positive, that means, what does that tell you about your original function? It's always concave up. Is our parabola always concave up? Yes. Now the IB exam and a fair number of questions like to do this sort of thing. They like to say, we hope that you've learned all the steps for sketching a graph. That you know that you could take your first derivative and do this sine diagram to find out where your graph is increasing and decreasing because of where your derivative is positive and negative. And we hope you can do your second derivative and find out where things are concave up and concave down. If you know that process, if we give you a question that's in a different order, could you work with that to get the other parts of it? Could you use just the picture of the original graph sort of works backwards to find out, well, what would the derivative look like? What would the second derivative look like? Okay, I'd like you to try this one. Put up the answer in a bit. So here, our blue graph would be the derivative, and our red graph would be the second derivative. How would we start? We would start by noticing our maxes and mins. Those are going to be equal to 0 because the slope of the tangent at those points is going to be 0. If you did your sine diagram and had those 2 points on your sine diagram, what does our original graph do? It goes up, then down, then up. That tells us that our derivative is positive here, negative here, and positive there. Personally, when I have two x-intercepts like we have here, what I would start with is drawing the negative part between them. I don't know how far down it's going to go, but I know that that section has to be below the y-axis. And then these parts on the left and right have to be positive. Maybe you recognize that your original graph was an x cubed graph, so it made sense that after you did your sine diagram that your derivative graph would be a parabola. Then, once you've got that graph of the parabola, you could take your parabola's graph and say, here I have a minimum on my derivative, so on my second derivative, that's where it's going to equal 0. Or you might have also said, it looks like on my original graph that that's the point where I change from concave down to concave up. So if you're looking at your sign diagrams for your red graph, you could either use the minimum point as a key thing there and say that that's where it's equal to 0, and my parabola is going down before and up after, so that would cause my second derivative to go from negative to positive. Or when looking at your second derivative, you could have said, no, instead I'm looking at that point as an inflection point. And inflection points tell me about how my original graph is either concave up or concave down. I see that it's concave down to that point and then concave up after. So that also tells me that before this red point, this part of my graph is negative, and this part of my graph is positive. Other things that can help you, you started with an x cubed, so the first derivative would be a parabola. Your second derivative would be a line. Here's our third one. Now we're given the graph of the derivative, and you want to graph the original. All right, check how he did. So in this graph, now we've got our derivative graph. What do we know about our derivative graph? We know that it is equal to 0 at -2, 0, and 3. We know that our derivative graph was positive in this section. Can you see between -2 and 0, it's below the y-axis, so negative there, then positive here, then negative there. So as far as our original graph, it's telling us that our original graph is going to be increasing, then decreasing, then increasing, then decreasing. So we know that we have a max at -2, a minimum at 0, and a max at 3. We also can see from our derivative graph that where we have a maximum and minimum, that these are going to be inflection points on our original graph. So we know that it's going to change from concave up to concave down. What we don't know from this graph is we know that there's going to be a maximum, a minimum, and a maximum. We can't necessarily tell exactly how high those maximums are going to be or how low those maximums are going to be. So when we're drawing the sketch, we're sort of estimating this is where I think the height of that point could be. But it could be anywhere. Because let's, for example, pretend that the equation of this blue graph, right now, the way that I have it written, I'm going to write it in factored form. It looks like it has an x-intercept at maybe negative 2.5. So then one of the factors would be x plus 2.5. It looks like it has one at x equals 0, so then a factor would be just x. And it looks like it has one at 3.5. And since our graph is bouncing off the axis there, we know that the multiplicity of this 0 would be squared. And that would be an x to the 4 graph. And if you did the derivative of that x to the 4 graph, you would get an x to the cube graph. If I added 7 at the end, what would that do to my original graph? Horizontal translation, 7 units up, right? If you took the derivative and you had an extra plus 7 at the end, what would that do? Nothing. That derivative would be exactly the same. That plus 7 won't make a difference. So we could have had this exact same blue graph moved up 7 units, and it would be the right answer. Because we would get the exact same derivative whether it was moved up 7 or not. So what we're looking at when we're doing these sketches is, do we have maximum and minimum points at the right x values? Do we have our graph increasing and decreasing in the right way? But exactly where those maximum and minimum values are, we can't tell unless we had more information. Okay, one more for you to try. Now we're working all the way backwards. We start with the second derivative and move up to the original function. All right, so there is the first derivative and the original function. How do we get that? Well, first of all, if you look at your second derivative, you have that your second derivative is equal to 0 there. That tells you two things. Well, I don't know if it's at, I don't know the value. But the fact that your second derivative is equal to 0 at that point is going to tell you something about the concavity of your original function, and it's going to tell you something about increasing and decreasing for your derivative graph. So when we look at our black line here, we notice that it's negative, then positive, negative, then positive. If we were just working backwards one step, right? Negative would tell us that the graph above it is going from decreasing to increasing. That's going to help us with our blue graph, because going up one level from our second derivative takes us to our first derivative. And in our green graph, it's going to tell us that there's an inflection point and that we're going to change from concave down to concave up. With our blue graph, we would know that that's a minimum. And sure enough, at that point, we make a minimum value. And if it's decreasing before and increasing afterwards, here we have the shape of the parabola. If you think that your original function is some sort of linear function, it would make sense that your derivative is some sort of parabola. And if you think your derivative is some sort of parabola, it would make sense that your original function is some sort of cubic function. But now that we've drawn our derivative, we can use these 2 points, where a derivative is equal to 0, to find out where we have maximum and minimums. And in between those 2 points, our function is negative. On either side, it's positive, so that tells us our original function is increasing, then decreasing, then increasing again. telling us that on our green graph, this is a max and this is a min, and so we get these points here. All right, let's work through, we've done a couple of these on your own. Let's work through example 5 together. So for 5, you have the diagram where A is a maximum and B is a minimum. You've got the x-coordinates where that happens. Sketch the graph of the derivative. Well, you would know then at -2 and at 6, since that's where our maximum and minimum are, those would be equal to 0. And if you had your sign diagram off to the side with -2 and 6, we could say, I can see in my original function that it's increasing to point A, then decreasing to point B, and then increasing after. That means that my derivative is going to be positive, then negative, then positive. Again, I find starting with the section between the 2 points the easiest to work on. If that's negative, that means this part has to be down here below. I don't know how deep it goes, how far down that graph goes. I could estimate it, right? If I wanted to give an estimate for how far this goes, I could look at that point on my original graph, draw a tangent line, and say, I think the slope of that line looks like -6, or I think the slope of that line looks like -5, and then mark that at -5. That could be a way to get a more accurate graph. But again, I'm just using an estimate, and again, using the idea, what does the derivative mean? It's the slope of all the tangents at any point. And there we have, so that would be enough as a sketch. We don't know that this is at -5. So I'm going to erase it, so if you weren't listening, you're like, oh, how does he find out that's exactly -5? I was just making an estimate. Write down the following from least to greatest. What do we know about f of 0? If we had to estimate it, it looks like it's at about +2. I'm just picking numbers. What do we know about f prime at 6? F prime, that's your derivative, that's your slope of your tangent. At 6, we have the minimum. What would that mean our derivative is equal to? That one I know for sure is equal to 0. F double prime at -2. At -2, what does f, the second derivative, tell us about? Concavity. At -2, can you see that things are concave down? Does that make you happy? No, it makes you sad. That means it's negative. So as far as ordering these from least to greatest, you'll know that f double prime is going to be negative, so that's your smallest one. F prime of 6 is equal to 0. And f of 0, we're just estimating it there. What we do know about it is it's a positive number.